Okay, in the last video, we saw that if we had this function f of z, then there was a certain point, z equals 1, where this function blew up to infinity. And we said that we could figure out the domain in which our Taylor expansion of this function is convergent by drawing this circle of convergence, centered where we took our Taylor expansion, z equals 0, and inflated to where we hit our first pole. And this point, z equals 1, where our function blows up to infinity, is called a pole. So, we said our Taylor expansion is convergent everywhere inside of this circle, and I'm going to write down a definition. It's a word you might have seen come up, but it's going to be the jargon we use to describe this property. This property is analyticity. So, I'm going to write down the definition and then we'll talk about it. All right, so if f of x is differentiable everywhere in a region, then it is analytic in that region. So f of z is analytic inside our circle of convergence. There's another word that's often used interchangeably with this, interchangeably with analytic, and that would be the word holomorphic. For our purposes, we're going to treat these as interchangeable. There are subtle differences. It depends on the Laurent expansion, but we're not going to get into all those details. So for our purposes, these two mean the same thing. All right. Differentiable is not exactly the lens that we were viewing this through. We were thinking more about poles, but it is a general requirement. If our function is going to be differentiable, there's a few things on our checklist that have to be met. The first one, as we said, is no poles in the region. So we stop expanding our circle of convergence when we hit a pole because our region, where the function is analytic, cannot contain a pole. Our Taylor expansion, we have to evaluate derivatives of our function at the point where we're interested in. And so if we have a pole, the value of our function blows up to infinity if we evaluate it at that point. So our function is not differentiable and cannot be evaluated at the location of our pole or singularity. Differentiability is a bit more strict. We also have to have a function that's generally differentiable. So, for example, if we had f of x equals absolute value of x, this function is not differentiable with respect to x because there's a cusp at x equals 0. Similarly, if I wrote f of z equals absolute value of z, I can rewrite this as the square root of z and z bar. Z and the complex conjugate of z. Because f of z depends not only on z, but also on the complex conjugate of z, if we take the derivative with respect to z, we're not capturing the full multitudes of this equation. So, our function also has to be differentiable, and so we can say it cannot be something like f of z bar. So, generally, if these two things are true, our function will be analytic in that region. Analyticity is an important property. It's going to be a prerequisite condition for the tools we're going to develop in the next video. But today we're going to look at some properties of our function that must be true if it's analytic. Okay, so I'm going to come over here and we're going to take some derivatives. First off, we're going to start thinking of our function f of z. And since z can be written as x plus iy, that means that f of z could also be thought of as f of x or y. Since we have a real part of our complex number x and an imaginary part y, our function could depend on either of those parts individually. So we could write it as f of x comma y. All right, so if we wanted to take a partial derivative of this function f with respect to x, that would be equal to the total derivative of f with respect to z, partial z, partial x. And we'll go ahead and simplify this. Our partial derivative of z with respect to x, if we look at our complex number definition, dz dx is just going to be 1. So we can drop this term, just write it as total derivative of f with respect to z. All right, we'll do this again for y. Partial f, partial y is equal to the total derivative of f with respect to z, partial z, partial y. And so this is going to be similar, but when we take partial z with respect to y, we hit that imaginary unit. So this will be equal to I df dz. All right, we will end up equating these in just a moment, but we're going to take more partial derivatives and see what more we can get into. Our complex numbers are generally separable into real and imaginary parts. And so, if we wrote out our complex function, f of z, our complex function can also be split into real and imaginary parts that both depend on the real and imaginary part of our complex number z. So the function has real and imaginary parts. Our complex numbers that go into those sub-functions also have real and imaginary parts. So we could write this, the real part as u of x comma y, the imaginary part as I times v of x comma y, and we should be able to separate our function into something that looks like this. So now, if we take more partial derivatives of f with respect to x and y, evaluating these the same way with our new definition, we'll get even more partial derivatives. We can equate them all together and see what relations pop out at the end. So if we take the partial derivative of f with respect to x, we have to distribute it across both of the properties, both of the portions of our function. So that'll be partial u, partial x, plus I times partial v, partial x. And we can do the same thing with our y, df, dy, or partial f, partial y. And it's going to look the same as the one I just wrote, except all of our x's will be subbed out for y's. Okay, so to progress further, what we're going to want to do is we're going to want to take each of these ways of describing our partial derivative and set these equal to each other. And so I'm just going to continue this on the right side here. So partial f partial x is equal to our total derivative of f with respect to z. Partial f partial y is going to be equal to I times our total derivative with respect to z. And so, since our next step is going to be equating both of these lines together, I'm going to go ahead and divide both sides by this I. So if I do that, the I will disappear from here. We're evaluating 1 over I times this line, or this line times a 1 over I. So the effect that this has is it will cancel the I on our second term. And 1 over I, we could rewrite this, multiply it times I over I. This is equal to minus I. All right. So if I rewrite this in its simplified form, we will end up getting minus I partial u partial y. This I will disappear, plus partial v partial y is equal to that total derivative df dz. So the last step that we're going to do here is we're going to take our two definitions for the total derivative and set them equal to each other. And if we do that, you'll notice this first definition has a real portion, partial u partial x, and an imaginary portion, partial v partial x. The second definition also has a real portion and an imaginary portion. And if these two definitions are equal, then the real part should be equal to the real part, and the imaginary part should be equal to the imaginary part, because these functions are separable. So I'm going to equate the real parts and the imaginary parts. I'm going to write them right here in the middle. So the real part of this first one is just partial u partial x, and that's equal to the real part of our second definition, partial v partial y. The next one, we equate the imaginary parts, and you could leave the i's in, but they'll cancel out. So we should have partial v partial x from our first definition, and then is equal to negative partial u partial y. I'm going to put a big box around these. These are what's called our Cauchy-Riemann equations. If our function is analytic, then these relations are going to be true. And it's a two-way street. Maybe you don't know if your function is analytic. Maybe you can't tell from looking at the form of your function whether you have poles or not. So a good way to check if your function is analytic, if you're not sure, is to evaluate these partial derivatives of the closed form of your complex valued function. If they work out to be true, then that means you can conclude that as long as these hold, your function will be analytic.